soil resistivity is a measure of how much the soil resists the flow of electricity. It is a critical factor in design of systems that rely on passing current through the Earth's surface. An understanding of the soil resistivity and how it varies with depth in the soil is necessary to design the grounding system in an electrical substation, or for lightning conductors. It is needed for design of grounding electrodes for high-voltage direct current transmission systems. In single-wire earth return power transmission systems, the earth itself is used as the path of conduction from the end customers back to the transmission facility. In general, there is some value above which the impedance of the earth connection must not rise, and some maximum step voltage which must not be exceeded to avoid endangering people and livestock. The soil resistivity value is subject to great variation, due to moisture, temperature and chemical content. Typical values are, usual values, from 10 up to 1000, exceptional values, from 1 up to 10,000. The SI unit of resistivity is the ohm meter. In the United States the ohm centimeter is often used instead. A wide range typical soil resistivity values can be found in literature. Military Handbook 419 contains reference tables and formulae for the resistance of various patterns of rods and wires buried in soil of known resistivity. Being copyright-free, these numbers are widely copied, sometimes without acknowledgement. Measurement. Because soil quality may vary greatly with depth and over a wide lateral area, estimation of soil resistivity based on soil classification provide only a rough approximation. Actual resistivity measurements are required to fully qualify the resistivity and its effects on the overall transmission system. Several methods of resistivity measurement are frequently employed. Ueno Method. The Ueno 4-pin method, as shown in figure above, is the most commonly used technique for soil resistivity measurements. Using the Ueno method, the apparent soil resistivity value is where I.E. equals measured apparent soil resistivity, A equals electrode spacing, B equals depth of the electrodes, RW equals Ueno resistance measured as VA in figure if B is small compared to A, as is the case of probes penetrating the ground only for a short distance. The previous equation can be reduced to Schlumberger method. In the Schlumberger method the distance between the voltages probe is A and the distances from voltages probe and currents probe are C. Using the Schlumberger method, if B is small compared to A and C greater than 2A, the apparent soil resistivity value is where I.E. equals measured apparent soil resistivity, A equals electrode spacing, B equals depth of the electrodes, C equals electrode spacing, RS equals Schlumberger resistance measured as VA in figure. Conversion between measures using Schlumberger and Ueno. The conversion between values measured using the Schlumberger and Ueno methods is possible only in an approximate way. In any cases, for both Ueno and Schlumberger methods the electrode spacing between the currents probe corresponds to the depth of soil investigation and the measured apparent soil resistivity is referred to as soil volume as in figure aside. The current tends to flow near the surface for small probe spacing, whereas more current penetrates deeper soils for large spacing. Thus, it is usually a reasonable approximation to assume that the resistivity measured for a given current probe spacing represents the apparent resistivity of the soil to a depth of when soil layer resistivity contrasts are not excessive. If the apparent soil resistivity measured with Schlumberger method i.e. is given, assuming that the soil resistivity are referred to a volume as in the figure aside with A equals L/3 follows. With where RW equals equivalent Ueno resistance, AW equals equivalent electrode spacing with Ueno method, as equals electrode spacing between voltages probe with Schlumberger method, C equals electrode spacing between voltages and currents probe with Schlumberger method. If the measured Schlumberger resistance is given, before to calculate the end values, the apparent soil resistivity has to be calculated as follows. The Ueno method is more laborious than the Schlumberger method because it requires many long measure cables, large free space, and for big electrode spacing one person per electrode is necessary to complete the survey in a reasonable time. However, the Ueno 4-pin method is the most efficient in terms of the ratio of received voltage per unit of transmitted current. the soil resistivity measurements have not to be affected by existing grounded electrodes. Buried conductive objects in contact with the soil can invalidate readings made by the methods described if they are close enough to alter the test current flow pattern. This is particularly true for large or long objects. Soil resistivity variability. Electrical conduction in soil is essentially electrolytic, and for this reason the soil resistivity depends on moisture content, salt content, temperature. Because of the variability of soil resistivity, IEC standards require that the seasonal variation in resistivity be accounted for in transmission system design. For practical purposes, when there are no other available information, in very cold regions, during the winter, a resistivity scale factor of 5 to 6 times the summer value would be an adequate average. Corrosion. Soil resistivity is one of the driving factors determining the corrosiveness of soil. The soil corrosiveness is classified based on soil electrical resistivity by the British standard BS 1377 as follow, i.e. greater than 100 I copyright M, slightly corrosive, 50, i.e. less than 100 I copyright M, moderately corrosive, 10, i.e. less than 50 I copyright M, corrosive, i.e. less than 10 I copyright M, severe. References